Hey y'all, so I'm going to be talking today about enzyme kinetics with you. This is chapter 12 in your book, and it's just going to be a brief overview look at enzyme kinetics. A lot of the information that we'll be talking about here, we've talked about in previous courses. However, the focus here is going to be more on understanding conceptual relationships between the different aspects of the kinetic relationship rather than mathematically figuring out what the actual numbers are. We can talk more about how the mathematical applications help us compare things in class. This is going to be more of a brief overview. So, to understand kinetics, when we discuss kinetics, what we're actually talking about is how fast the reaction moves forward. This means that V is a measure of how quickly the reaction can make the product, or it can use up the reactant. Mathematically, V is represented in the equations below. All three equations are going to be correct representations of V, however, they are different in terms of what they're measuring. And so the first equation, where V equals d concentration of P over dt, what that's looking at is how fast the product is formed over time. The second equation, which is negative ds dt, is looking at how fast we actually lose substrate. And then the third equation is something that I think everyone's a little bit more familiar with. This is the more classic representation of a rate equation, and this shows K times the concentration of S, and this is very important to note that this is little k, and this just shows how the reaction will proceed. And so one thing to also note here is that that last term, the K times the concentration of S, that equation can change depending on the reaction order, but we can talk more about that in class. The next equation that we're going to be looking at is an overview of the rate equations. So enzyme reactions are able to be analyzed with this equation, and as you guys see, there are a few more numbers and letters that we really haven't dealt with in the past. So this would be K sub negative 1, K1, and K2. As these in the equation, these are actually rates for the forward and backward equations that are shown there. And so we're able to understand that the enzyme plus substrate step moves forward to the enzyme substrate complex step. Then this can either dissociate back into the enzyme plus the substrate, or it can actually release the product, and then the enzyme is, of course, reformed. So if we have a larger K2, what that's going to tell us is that when we form the enzyme substrate complex, that's going to be more likely to proceed to give us product. However, if we have a larger K negative 1, when we have the enzyme substrate complex, what that's going to do is actually dissociate back into the enzyme and the substrate. We're going to see an overall reaction go from the E plus S to the ES to the E plus P if we have K1 and K2 larger than K negative 1. However, if, like I said, K negative 1 is larger than K2, even if it proceeds from E plus S to ES, we're going to fall back to the E plus S state. So one reason that this could happen is the E plus S is more thermodynamically favorable than the E plus P state if we are under thermodynamic limitations. And so even though we have an E plus S forming the ES, it doesn't want to go forward to form the E plus P state because that's thermodynamically unfavorable, and so it'll reform the E plus S phase. One thing that I want you guys to do as a class is try to figure out another example of why the K negative 1 would be greater than the K2, and so we'd see the enzyme substrate complex dissociate back into the enzyme and the substrate. Now we're going to move on to the Michaelis-Menten equation. This is in your book. I highly stress that you guys should learn this equation now. It'll be very helpful in understanding what we're talking about as the classes build on each other from here with enzymes. And so this really gives you a great look at how we can compare and contrast different values that are standardized so we can compare them across different enzymes. However, to use the Michaelis-Menten equations, there are a few assumptions that we need to make. And so the first assumption that has to be true for us to use these equations is that there's an assumption of equilibrium, and this states that the rate of the ES complex dissociating back into the E plus S state, rather than going to forward a product formation, is very, very small. And so what that means is, looking in your book, you'll see this. It actually means that K negative 1 is much, much less than K2. And so if we think back to the equation that we were looking at on the previous slide, that'll actually show that we're going to be moving forward. Finally, the second assumption that we have to make is the assumption of steady state. This says under physiological conditions, the substrate concentration is in great excess compared to the enzyme concentration. And so that tells us that the concentration of substrate has to be much greater than the concentration of enzyme. And so there's always going to be enzymes associated with the substrate. And so we don't have a situation where we have so much enzyme that we cannot actually saturate it. And that's pretty important for this as well, and we'll find out why later. So more about what we can learn from the Michaelis-Menten equations. From the equation on the previous slide, we know how to relate V0 and Vmax. V0 is the initial rate of the reaction, and so this is as the reaction just starts out, right at like the instantaneous moment that we set it into the beaker or in the cell or whatever we're looking at. This is the very first rate, like this is the very beginning of the reaction. Vmax is going to be the maximum rate of the reaction, and so as we look at the graph that we'll be looking at on the next slide, you'll see that it actually tapers off, and so it's kind of a hyperbolic curve that we're looking at, and you'll understand a little bit more once we get to the next slide. But we'll reach a Vmax, which shows maximum saturation of the enzyme, and so the enzyme is working as fast as it can, and all of the enzymes present are working on substrate as fast as they can. Additionally, looking at Km, this is an equilibrium constant under the Michaelis-Menten assumptions. Km is going to be the substrate concentration at half of the Vmax. And so this actually is going to be a great indicator of the enzyme affinity for the substrate. If you guys remember back to the hemoglobin binding curve, we knew that with a lower hemoglobin P50 value that shows higher affinity. It's very synonymous here, where if we have a low Km, we have a high affinity for enzyme binding to substrate. However, this Km can be changed by pH and temperature. Note that on this slide, when I say Km, I'm referring to big K, not little k. Big K represents an equilibrium constant. In this case, Km is called the Michaelis constant, while little k, such as K1, K2, and K-1, which is what we were looking at a little bit earlier, are actually considered rate constants. They're not the same K. So like I said, this is an enzyme saturation curve. We're going to be looking at this a lot. You can actually plot these once you have like a few points that you understand. And so what this shows is the maximum rate at which an enzyme can act on a substrate. And so if we have the x-axis is substrate concentration, the y-axis is the velocity of the reaction. And so you'll see once it tapers off, we consider the value just around there to be a Vmax. So if you take half of that Vmax and then carry that number over to the curve and drop it down to the substrate concentration, you're actually going to be able to find your Km value. This graph then was able to plot different intervals at 2 km, 3 km, and 4 km based on what the original Km is. And we will be able to do stuff like that in class. However, sometimes these curves are a little tricky because graphing hyperbolic functions are not always as easy as a linear function. And it's also hard to extrapolate as much data from them because you have to estimate a lot more. And so what scientists have actually done is started using the Lineweaver-Burk plot. This is the inverse of the Michaelis-Menten equation, and so what this does is it actually takes the equations that we were just looking at that helped form the hyperbolic curve, and it plots it onto a linear curve, which makes it a lot easier to deal with. So a few things that we need to note about this plot is that the x-axis intercept, which is going to be to the left of the y-axis, is a negative number, and this is whatever that axis intercept is actually going to be the negative inverse of the Km value. And so say the axis was crossed at -2, then our Km value would actually be negative 0.5. Actually, no, positive 0.5. I apologize. And so we'll go over some examples of that in class as well. And then the y-intercept is going to be a positive value on the Lineweaver-Burk plot, and this is just going to be the regular inverse of the Vmax. And so if we crossed the y-axis at say 1/3, then our Vmax is going to be 3, and that's some information that we would not have been able to gather as quickly or as accurately using the previous plots, because you have to use a little bit more of an estimation. Additionally, you can note that the slope of this line is actually Km over Vmax, and so that'll be able to help you when you're constructing plots like this to be able to analyze different Kms and Vmax values. So why do we use the Lineweaver-Burk plot? These are, like I said, a lot easier to extrapolate data from, and so it allows us to compare different enzymes or the same enzyme under different conditions a lot easier. It also, we'll talk about this more for next class, but it deals a lot more with inhibition and how can we inhibit enzymes with different competitive, mixed, or non-competitive inhibitors. This is actually going to change what we're seeing on the graph. And so what I want you guys to see over here on the right is that under different conditions, we're either changing an x-intercept, we're changing a y-intercept, or we're changing both. And so what does that mean for our Vmax and Km values? Just think about that so when we get into class, we can talk about it. And finally, we have catalytic efficiency. For that, we're going to need to consider Kcat and Km. Kcat is little k, and Km is big K, so let's not get those confused. But Kcat is the turnover rate of the reaction. That means how fast can an enzyme do its reaction on the substrate and then move on to do another reaction on another substrate. And so that's calculated by looking at the Vmax over the concentration of enzymes overall. And so if you want to make a high Kcat, what you can do is you can either decrease the overall enzyme total concentration, or you can increase Vmax. Now, actually doing that is pretty difficult because we can't change too much of that, but Kcat is just the ratio of the Vmax of the reaction compared to the overall concentration of enzyme. Additionally, we have catalytic efficiency, and this is going to be the ratio of Kcat to Km. This is where we're able to really compare a lot of things because it tells you how efficient the enzyme is acting on the system. And so if you want to make the catalytic efficiency as high as possible, what are you going to do there? Well, two ways are going to be to increase the Kcat as much as possible or decrease the Km as much as possible. So when we come into class, we're going to talk a little bit more about how to do that effectively, and that will be able to tell you a lot more about how we can compare different things together.